All right, we're going to look at a little interactive online through the Exploratorium called Your Weight on Other Worlds. And so this is a little chance to explore how gravity affects your weight. There is some math, an equation entered, but you're not going to have to know how to solve anything. The first thing you're going to do is enter your weight and then click calculate. After you do that, your weight on other planets and moons and stars will show up. And what I'd like you to notice is that depending on the planet that you're on, your weight is different. On Earth, your weight is 100 pounds. And so then you can take a look at what it is on the other planets. You probably remember that Jupiter is one of the biggest planets, or is the biggest planet in our solar system. And you'll notice that your weight is heaviest on Jupiter. Pluto, which is a dwarf planet, not even considered a planet anymore, your weight would only be 6.7 pounds. Some of Jupiter's moons would give you different weights. All of them would give you different weights. Notice that the weights depend on a couple of things. We're going to get to what that depends on in the reading. This gives you your weight on stars, and this is a joke. Better land at night to avoid burning your feet. If you don't understand why that is a joke, ask me. A neutron star, your weight would be this huge number. A white dwarf, and even on the sun, if you weighed 100 pounds on Earth, your weight on the sun would be 2,707 pounds. To understand a discussion of weight, you need to kind of understand the difference between mass and weight. And so I'm going to read through this article and try and explain some of it as we go. Mass and weight. Before we get into the subject of gravity and how it acts, it's important to understand the difference between weight and mass. We often use the terms mass and weight interchangeably. That means we substitute them for each other, even if they're not really things that we could swap. We often use the terms mass and weight interchangeably in our daily speech, but to an astronomer or a physicist, they are completely different things. The mass of a body is a measure of how much matter it contains, and matter is just how many atoms you contain. An object with mass has a quality called inertia, and that's that word inertia. You may have heard it, but it's kind of a tricky one to know. If you shake an object like a stone in your hand, you would notice it takes a push to get it moving, and another push to stop it again. If the stone is at rest, it wants to remain at rest. Once you've got it moving, it wants to stay moving. This quality or sluggishness of matter is its inertia. Mass is a measure of how much inertia an object displays. So something with large mass is harder to get moving and to stop once it's moving. Something with low mass is something that's easy to get moving. Weight is an entirely different thing. Every object in the universe with mass attracts every other object with mass. The amount of attraction depends on the size of the masses and how far apart they are. For everyday size objects, this gravitational pull is vanishingly small, but the pull between a very large object like the Earth and another object like you can easily be measured. How? All you have to do is stand on a scale. Scales measure the force of attraction between you and the Earth. The force of attraction between you and the Earth or any other planet is called your weight. So your weight is a combination of your mass, the atoms you contain, and the force of gravity on the planet where you're standing. And that's why your weight is different on different planets. If you're in a spaceship far between the stars and you put a scale underneath you, the scale will read 0. Your weight is 0. You are weightless. There's an anvil, which is a large metal object, floating next to you. It's also weightless. But are you and the anvil massless? Absolutely not. If you grabbed the anvil and tried to shake it, you would have to push it to get it going and pull it to get it to stop. It still has inertia and therefore has mass, yet it has no weight. Do you see the difference? So weight changes depending on the gravity of what you're near, or if you're being pulled on by gravity, but mass doesn't change. It's something that will stay the same. As stated above, your weight is a measure of the pull of gravity between you and the body you are standing on. This force of gravity depends on a few things. First, it depends on your mass and the mass of the planet you're standing on. If you double your mass, gravity pulls on you twice as hard. If the planet you're standing on is twice as massive or big, gravity also pulls on you twice as hard. On the other hand, the farther you are from the center of the planet, the weaker the pull between the planet and your body. The force gets weaker quite rapidly. If you double your distance from the planet, the force is 1/4. And that's because down here, radius is squared. That's what the R refers to as the radius, how far you are from the object. If you triple your separation, the force drops to 1/9. 10 times the distance, 1/100th the force. See the pattern? The force drops off with the square of the distance. And if we put this into an equation, it would look like this. F is the force of gravity. The two m's on top are your mass and the planet's mass. This R below is the distance from the center of the planet. The masses are in the numerator, the top of the fraction, because the force gets bigger if they get bigger. The distance is in the denominator, or the bottom of the fraction, because the force gets smaller when the distance gets bigger. Note that the force never becomes zero no matter how far you travel. Perhaps this was the inspiration for the poem by Francis Thompson. All things by immortal power, near or far, to each other hiddenly linked are, that thou canst not stir a flower without troubling a star. This equation, first derived by Sir Isaac Newton, tells us a lot. For instance, you may suspect that because Jupiter is 318 times as massive as the Earth, you should weigh 318 times what you weigh at home. This would be true if Jupiter was the same size as the Earth. But Jupiter is 11 times the radius of the Earth, so you are 11 times further from the center. This reduces the pull by a factor of 11 squared, resulting in about 2.53 times the pull of the Earth on you. Standing on a neutron star makes you unimaginably weighty. Not only is the star very massive to start with, it has about the same mass as the Sun, but it is also incredibly small, only the size of San Francisco. So you're very close to the center, and R is a very small number. Small numbers in the denominators of a fraction lead to very large results. So this formula here, which again, you're not supposed to have to use the math, but what it's telling you is the bigger the mass of the objects, those will make gravity increase as these get bigger. But you're dividing by radius squared down here, and radius is the distance of an object from the center to the center of the planet that it's on. And so the bigger R gets, the lower the force of gravity. So the farther away you are, the lower gravity is. And the heavier, or I should say more massive you are, the more the force of gravity is.